Spring 1940. As Nazi panzers thundered through France and the Luftwaffe dominated Europe's skies, a 45-year-old engineer named Edgar Schmued sat in a cramped North American aviation office in Englewood, California, sketching what would become the most important fighter plane of World War II. But here's the twist. Nobody asked him to design it. The U.S. Army Air Corps hadn't issued a contract. They hadn't even hinted they wanted a new fighter. Schmued was operating entirely on calculated risk, and if he got it wrong, his company would eat the costs, and he'd likely be out of a job. Edgar Schmued's story sounds like something straight out of Hollywood, except it actually happened. Born in Hagen, Germany, in 1899, he grew up watching the Wright brothers' demonstrations in Europe and became obsessed with flight. After World War I, he worked for Fokker in Holland. Yes, that Fokker, the firm that built the Red Baron's triplane. When the Great Depression struck, he immigrated to America in 1930 with nothing but engineering drawings and ambition. By 1936, he had landed at North American Aviation, a scrappy California outfit best known for training planes. They weren't Lockheed. They weren't Boeing. They were the underdogs. In April 1940, the British Purchasing Commission came knocking with an urgent request. Britain was losing aircraft faster than factory could replace them and needed fighters, lots of them, immediately. They asked North American to build Curtiss P-40 Warhawks under license. Save money. Standard procedure. But company president James Dutch Kindleberger and Schmued saw a different opportunity, a chance to leapfrog the competition entirely. Schmued told the British representative something outrageous. "We can design you a better fighter from scratch in 120 days. The Brits thought he was mad. His own colleagues thought he was mad. You didn't design a frontline combat aircraft in 4 months. It took years of testing, wind tunnel data, and failed prototypes. But Schmued had already been secretly exploring advanced fighter concepts, obsessed with one problem that plagued every Air Force on Earth: range. The Spitfire was superb in a dogfight, but ran out of fuel after 400 miles. The P-40 had decent range, but lacked climb performance. The German Me-109 was deadly, but chained to its airfields by tiny fuel tanks. Every nation faced the same cruel compromise. You could build a nimble fighter or a long-range one, but not both. Physics said it was impossible. Schmued believed physics could be persuaded with a right-wing design. Desperate and out of options, the British signed the contract on May 29, 1940. 120 days to first prototype. Impossible, or so everyone thought. Schmued gathered a team of 150 engineers and draftsmen and organized them into rotating 24-hour shifts. They didn't just build a fighter. They were about to build a legend. His secret weapon wasn't just caffeine and determination. It was data from NACA, the National Advisory Committee for Aeronautics. They'd been experimenting with a revolutionary wing design called a laminar-flow airfoil, and Schmued was about to stake his entire career on the idea that it would work not in a wind tunnel, but in combat at 400 miles per hour with enemy guns blazing. On October 26, 1940, just 178 days after the British contract was signed, test pilot Vance Breeze lifted the first NA-73X prototype off the runway at Mines Field in Los Angeles. The plane felt light, responsive, alive. Breeze rolled, climbed, dove, and when he landed, he told Schmued the words every engineer dreams of hearing. "This thing handles like a sports car." Within weeks, the British gave it a name, Mustang, and early reports seemed to confirm Schmued's impossible gamble. The aircraft was fast, 390 miles per hour in level flight, faster than nearly anything flying. It was smooth. It was stable. And then reality struck. When pilots took the Mustang into high-altitude combat, everything fell apart. The problem showed itself brutally in early 1942, when Royal Air Force squadrons received their first Mustangs. Below 15,000 feet, the airplane was magnificent. RAF pilots used it for ground attack and reconnaissance, strafing German supply convoys across France with devastating precision. But above 15,000 feet, the Mustang turned from a thoroughbred into a plow horse. The engine choked. Climb rate collapsed. In a high-altitude duel with a Messerschmitt Bf-109 or Focke-Wulf FW-190, the Mustang was a sitting duck. Pilots joked it was a low-altitude sports car trapped in a high-altitude war. The culprit was the Allison V1710 engine, a beautifully built piece of American machinery with one fatal flaw. It used a single-stage, single-speed supercharger. To keep it simple, at high altitude, air gets thin, starving engines of oxygen. A supercharger works like an air pump, forcing more oxygen into the cylinders. The Allison system performed well at sea level and medium altitude, delivering about 1,150 horsepower. But above 15,000 feet, the arena of European air combat, it simply couldn't compress enough air. Power dropped to around 900 horsepower. Meanwhile, German fighters with advanced two-stage superchargers maintained full power up to 25,000 feet. And in a dogfight, horsepower equals survival. Speed, climb, and the ability to run or chase. The Mustang had the aerodynamics, but not the muscle to use them. American pilots learned this the hard way. The U.S. Army Air Forces demoted their P-51s to low-level photo reconnaissance, the same role the IAF had adopted. Mustang pilots screamed across enemy lines at treetop height, relying on speed and surprise to survive instead of engaging in combat. It was humiliating for design that looked so promising. Engineers at Wright Field, Ohio, tested every fix they could imagine: fuel mixtures, supercharger gears, propeller pitch, but you can't squeeze performance that doesn't exist. The Allison simply wasn't built for high-altitude warfare. North American's brilliant A-frame was being strangled by an underpowered heart. By mid-1942, the Mustang program looked like a costly mistake. The Army had ordered thousands, but what use was a fighter that couldn't fight at bomber altitude? Over Europe, B-17 flying fortresses were being shredded, dozens lost on every raid. Because their escorts, P-47 Thunderbolts and P-38 Lightnings, couldn't go the distance. Once they turned back, the bombers were left alone, and Luftwaffe fighters tore them apart like wolves among sheep. Everyone knew the answer: a long-range, high-altitude escort fighter. The Mustang had the range. It had the design. But it couldn't breathe at 25,000 feet. Schmued's masterpiece was suffocating. The solution came from an unlikely source, a British test pilot named Ronald Harker, visiting North American's Englewood factory in April 1942. Harker flew for Rolls-Royce, testing Spitfires and new engine variants. When he took a Mustang up for a demo flight, he instantly recognized what the Americans had missed. The A-frame was extraordinary, the best he'd ever flown, but it was gasping for air. As soon as he landed, he sent a telegram to Rolls-Royce headquarters in Derby, England. 5 words that would change aviation history. Flight testing Mustang needs Merlin engine. The Rolls-Royce Merlin wasn't just any engine. It was the beating heart of the Spitfire and the Lancaster bomber, and it had what the Mustang desperately lacked: a 2-stage, 2-speed supercharger that held full power up to 30,000 feet. The setup was ingenious. The first stage compressed the air, an intercooler cooled it, and the second stage compressed it again before it hit the cylinders. The result: 1,520 horsepower at 20,000 feet, nearly twice the Allison's output at that height. But installing it wouldn't be simple. The Merlin was heavier, mounted differently, and required new engine supports, cooling systems, and propeller configurations. Rolls-Royce didn't wait for paperwork or permission. By October 1942, they pulled a Mustang from IAF stock and shoehorned a Merlin 61 engine into it at their Hucknall facility. On October 13, 1942, test pilot Captain Ronnie Shepard took it up. He climbed to 20,000 feet, expecting the usual struggle, and instead, the Mustang exploded forward like it had been unchained. He pushed to 25,000 feet and smiled. The legend had finally found its heart. Still climbing strongly, the engine was pulling hard at 30,000 feet. When Shepard dug back down and opened the throttle, the A-speed indicator hit 433 miles per hour. He landed and filed a report using words like phenomenal and revolutionary. The British immediately christened the A-craft the Mustang X and marked it top priority. Back in America, North American aviation and the U.S. Army Air Forces were scrambling to catch up. Rumors of the British Merlin test had already reached them, and in November 1942, Wright Field received the official performance data. The numbers looked unbelievable: a 50-mile-per-hour speed increase and a service ceiling jump from 31,000 feet to 41,900. Some engineers thought it had to be a measurement error. Then, On November 30th, 1942, the first American-built Merlin Mustang, designated XP-51B, took flight from Englewood, California. Test pilot Bob Chilton ran it through its paces and radioed down, barely containing his excitement. "This thing climbs like a homesick angel." The transformation was total. The same A-frame that gasped above 15,000 feet now ruled the skies at 25,000 and could fight effectively above 35,000. Packard Motor Company in Detroit began producing Merlin engines under license. The Packard V1650, an American-built Merlin redesigned for mass production. By early 1943, P-51B Mustangs with Packard Merlins were rolling off assembly lines at both Englewood and a new plant in Dallas, Texas. The old Allison Mustangs were quietly reassigned to ground attack and reconnaissance duties. The real Mustang, the one that would escort bombers to Berlin and back, had finally arrived. Schmued's A-frame had found its perfect heart, and the Luftwaffe was about to learn what 1,500 horsepower paired with laminar-flow wings could do in the hands of skilled pilots. Now, let's talk about the true magic behind Schmued's design: the wing. This is where most people's eyes glaze over when engineers start talking about boundary layers and Reynolds numbers. But stay with me, because this is the difference between a good fighter and a legend. Every airplane wing drags a thin layer of air molecules along its surface. Normally, that air becomes turbulent, tiny whirlpools and eddies swirling chaotically over the wing. Turbulence means drag, and drag means wasted fuel. Schmued's mission was to eliminate as much of that turbulence as possible. Enter the NACA 45-100 series laminar-flow airfoil, developed by engineer Eastman Jacobs at the Langley Research Center in Virginia during the late 1930s. Jacobs had spent years testing airflow in wind tunnels and discovered something counterintuitive. Most 1930s aircraft wings had their thickest point about 25 to 30% back from the leading edge. Jacobs moved it to 45%, nearly halfway down the wing chord. That subtle change reshaped the pressure gradient, keeping airflow smooth and laminar, meaning organized, layered flow instead of chaotic turbulence, over much more of the wing surface. The results were stunning. Wind tunnel tests showed laminar flow wings could reduce drag by 30 to 40% compared to traditional airfoils at cruise speeds. That meant 30% less drag, 30% less fuel burned, or 30% more range. But there was a catch. Laminar flow only worked if the wing surface was perfectly smooth. We're talking tolerances measured in thousandths of an inch. A single rivet head, a bug splatter, or even rough paint could trip the airflow into turbulence and erase the advantage. Most engineers said it was impossible to maintain that level of precision in mass production, let alone in combat conditions with bullet holes and field repairs. Schmued disagreed. He obsessed over manufacturing tolerances that seemed insane for 1940. North American developed flush riveting techniques, so rivet heads sat level with the skin. They used precision jigs and fixtures to hold panels within plus or minus 0.05 inches. Workers hand-sanded the wings and applied multiple coats of primer and paint, wet sanding between each layer until the surface shone like glass. Inspectors rejected wings that other companies would have accepted as flawless. It added time and cost, but the payoff was massive. The P-51's internal fuel capacity was 269 gallons, later boosted to 489 with external drop tanks. That gave it an effective combat radius of about 750 miles, enough to fly 750 miles, fight for 20 minutes, and return home. Compare that to the Spitfire Mk9, with just 85 gallons and a 400-mile radius, or the P-47 Thunderbolt, with 305 gallons and 475 miles. The Mustang wasn't just better, it was in a different league. And here's the elegant irony. Because the laminar flow wing was so efficient at high speed, the Mustang actually flew farther by flying faster. At a 280 miles per hour cruise, it sipped fuel so efficiently that external tanks turned it from a tactical aircraft into a strategic weapon. Bomber crews began calling them little friends, because for the first time in the European Air War, those little friends could stay with them all the way to the target, and all the way home. March 4, 1944. 64 P-51B Mustangs from the 4th Fighter Group lifted off from Debden Airfield, England, at 10:15 a.m., their wings heavy with 110-gallon drop tanks. The mission briefing was simple and historic. Escort the B-17 bombers to Berlin and bring them back. Berlin, Hitler's capital, 1,000 miles round trip. A 1,000-mile round trip deep into the heart of the Third Reich, territory no Allied fighter had ever dared reach. The bomber crews could hardly believe it. They'd seen too many escorts waggle their wings in farewell and turn back at the German border, fuel nearly gone, leaving them alone as a Luftwaffe swept in for the kill. But this time would be different. Lieutenant Colonel Don Blakesley led the formation, a combat veteran who'd flown Spitfires with the IAF before joining the U.S. Army Air Forces. Blakesley knew exactly what this mission meant. If the Mustangs could reach Berlin, the Luftwaffe would have nowhere left to hide. German squadrons had been retreating deeper into Reich territory, operating from airfields they believed safe from American escorts. Berlin was both the psychological and operational heart of the Nazi air defense. If you could fight over Berlin, you could fight anywhere. The weather was classic March misery, thick clouds over the channel and heavy icing at altitude. A few Mustangs turned back with mechanical issues, but the main force pressed on. They crossed into German airspace at 27,000 feet, throttling back to conserve fuel. The bomber stream stretched for miles, 316 B-17s bound for a ball-bearing plant in Aachen, just outside Berlin. Around 11:40 near Brunswick, the first German fighters appeared, Messerschmitt Bf-109GS and Focke-Wulf Fw-190 as diving from above. Normally, this was when the escorts would already be gone, but not today. The Mustangs were still there, and the German pilot hesitated. Years of habit told them American fighters couldn't possibly be this far east. That hesitation proved fatal. The Mustangs broke formation and engaged, diving and climbing with deadly precision. Their superior high-altitude speed let them dictate the fight. Captain Don Gentile shot down 2 Bf-109s in 3 minutes, using the Mustang's incredible climb rate to gain altitude, then slashing downward in gravity-assisted dives. Schmued's laminar-flow wings kept the aircraft stable even at extreme speeds that made other fighters buffet and shake. For the first time, German pilots found themselves being both outclimbed and outrun. The fur ball, pilot slang for a massive, chaotic dogfight, spread across 50 miles of sky, but one fact stood out. The bombers kept flying toward Berlin, and the Mustangs stayed with them. By 12:15, the formation reached Berlin's airspace. Flak batteries erupted, black bursts peppering the clouds, but the weather worked in the Allies' favor. The cloud cover was so thick the gunners were firing blind. The B-17s dropped their payloads through the overcast using radar guidance and turned west. The Mustang pilots checked their fuel gauges, dropped tanks empty, internal fuel left for the return leg. The math still worked. They throttled back to cruise and held steady for home. By 14:30, the formation crossed the North Sea. By 3 p.m., wheels were touching down on English runways. The numbers told the story. 5 bombers lost, mostly to flak. The Luftwaffe claimed 11 Mustangs destroyed, but actual losses were 5, with 3 pilots rescued. American fighters claimed 13 German aircraft downed. Yet the real victory wasn't the kill ratio, it was psychological. Luftwaffe pilots radioed their controllers in disbelief. American fighters over Berlin. Reichsmarschall Hermann Göring, commander of the Luftwaffe, reportedly muttered, "When I saw Mustangs over Berlin, I knew the war was lost." The myth of Fortress Germany had died that day, 27,000 feet above the capital, thanks to Edgar Schmued's impossible wing design. But reaching Berlin was only half the battle. The Mustang had to survive there, too. And this was where Schmued's engineering genius paid off in ways no one had predicted. By 1944, German fighter pilots were no amateurs. Many were seasoned aces, veterans of the Battle of Britain in the Eastern Front, flying machines purpose-built for interception. The Messerschmitt Bf-109G could hit 400 miles per hour and climb, at 3,100 feet per minute. The Focke-Wulf Fw-190A was even more formidable, a rugged, radial-engine brute that could absorb punishment and roll faster than anything else in the air. On paper, they were equals. In practice, the Mustang made even veteran German pilots look outclassed. The P-51D, introduced in mid-1944, featured a bubble canopy for full 360-degree visibility and could reach 437 miles per hour at 25,000 feet. That was fast, but not dramatically faster than the German fighters. The real advantage was climb rate, 3,200 feet per minute. With a Merlin engine roaring at war emergency power, altitude was life. Whoever climbed higher first controlled the fight, diving for attack or breaking away safely. The Mustangs could match the Germans' climb, and then keep going when their opponents' engines began gasping for air. The two-stage Merlin supercharger breathed effortlessly at 28,000 feet, giving the P-51 an edge no Luftwaffe plane could match. Turn performance was another decisive factor. It separated good fighters from great ones. The Mustang's laminar-flow wing allowed it to sustain a tight turn radius, roughly 1,200 feet at 300 miles per hour, without bleeding off excessive speed. It could whip around in a tight circle and still keep its energy. The FW-190 turned wider. The BF-109 could turn tighter initially, but it lost speed too quickly, leaving its pilot vulnerable in the next pass. The Mustang could do it all: turn, climb, dive, and run, with power to spare and range to burn. Rapidly, leaving the pilot exposed, American pilots learned to exploit that weakness. If a Messerschmitt got on your tail, you'd pull into a climbing spiral turn. The 109 would follow, both aircraft pulling 4 or 5 GS, enough to gray out your vision. But the Mustang held its energy better. After 2 full turns, the 109 would begin to wallow, slow and vulnerable, while the Mustang still had speed to spare and could reverse the fight. Diving speed also mattered enormously when things went wrong. The Mustang was cleared for dives up to 505 miles per hour, though pilots often exceeded at chasing German jets. The airframe stayed solid, no flutter, no control lockup. Schmued had built strength into every inch using stress skin construction, where the aluminum skin itself carried aerodynamic loads instead of relying only on internal structure. German fighters, especially the 109, suffered elevator flutter in high-speed dives, forcing pilots to ease up past 450 miles per hour. That 50 miles per hour edge meant a diving Mustang could catch nearly any fleeing opponent or escape almost any pursuit. Firepower completed the picture. The P-51D mounted 6.50 caliber Browning M2 machine guns, 3 in each wing, with 1,880 rounds total. Each gun fired 800 rounds per minute, and at convergence distance, about 300 yards, all 6 streams of bullets met in a 6-foot-wide cone of destruction. A 2-second burst sent roughly 160 rounds into that cone, more than enough to tear apart the light frames of German aircraft. Pilots reported seeing wings shear off, tails rip away, and cockpits vanish under concentrated .50 caliber fire. The Mustang wasn't just faster and more agile, it hit far harder. German aces who had survived years of combat suddenly found themselves outclassed by American pilots with barely 50 hours of experience because the Mustang gave those rookies the tools to offset their inexperience. That's the mark of great engineering, making the impossible seem routine. Then came the moment when thousands of these fighters entered combat, flown by men told their mission wasn't to chase kills but to bring the bombers home. That doctrinal shift, combined with the Mustang performance, turned the skies into a slaughterhouse. Between January 1944 and May 1945, P-51s destroyed roughly 4,950 enemy aircraft, more than any other Allied fighter in Europe. Of those, 4,131 were shot down in aerial combat, and 819 destroyed on the ground during strafing runs. But the numbers only hint at their true effect. The 8th Air Force had been losing about 350 heavy bombers per month in late 1943, nearly 3,500 crewmen killed or captured every 30 days, an unsustainable pace. Each B-17 or B-24 carried 10 men, cost hundreds of thousands of dollars, and required months of training. The Luftwaffe had been winning the attrition war simply by forcing unescorted bombers to fly through concentrated fighter corridors guarding key industrial targets. In October 1943, the Schweinfurt-Regensburg raid lost 60 bombers out of 291, a 20% loss rate that threatened to end the bombing campaign entirely. The arrival of long-range P-51B escorts in December 1943 changed the equation overnight. By March 1944, bomber losses dropped to 3.5% per mission. By June, after D-Day, when Mustang groups were flying multiple sorties daily, losses fell below 2%. The Luftwaffe hadn't grown less capable. It had been forced into an unwinnable position. German fighters had to engage to protect their factories, but engaging meant facing Mustangs that could chase them anywhere. Luftwaffe pilots began reporting bomber formations they couldn't attack because Mustangs held the altitude advantage. Escort missions had turned offensive. Ground attack operations added another layer of devastation. Once the bombers were safely headed home, Mustang squadrons would drop to treetop height and hunt anything that moved: locomotives, trucks, depots, or parked aircraft. The same .50 caliber guns that shredded fighters at altitude chewed through ground targets with ease. German-trained engineers learned to jump from their cabs the instant they spotted Mustangs, knowing a single pass could turn a locomotive into wreckage. Luftwaffe airfields tried dispersing aircraft into blast pens or satellite strips, but that only made operations harder. The Mustang forced the entire German air defense network into a permanent reactive stance. The price was steep. The 8th Air Force lost about 2,520 Mustangs from 1943 to 1945, with roughly 1,300 pilots killed, a 33% loss rate against enemy aircraft destroyed, favorable but costly. Many of those losses came from flak and small arms fire during low-level strafing missions, the most hazardous role of all. A single rifle round through a radiator could doom a Mustang, bleeding coolant until the engine seized. Yet the arithmetic of war was merciless and clear, trading one fighter pilot for 2 or 3 German planes, and saving dozens of bomber crewmen, was a bargain the Allies had no choice but to accept. To win the war. By the spring of 1945, the Luftwaffe had been reduced to a ghost force, flying sporadically with little fuel and green pilots who barely had 30 hours in the air. The Mustang hadn't single-handedly won control of the skies, but it made victory certain, and faster by months. When the war ended in May 1945, most wartime aircraft were scrapped or sent to museums within a few years. The future, everyone agreed, belonged to jets. The Messerschmitt Me 262 had already demonstrated that piston engines were obsolete, even if it came too late to save Germany. Yet Edgar Schmued's Mustang refused to fade quietly into history. The innovations built into its laminar-flow wing and stress-skin fuselage kept inspiring engineers long after the last European mission. What happened next revealed something profound about true innovation. Great design transcends its original era. When the Korean War erupted in June 1950, the Air Force suddenly needed durable ground attack planes that could take off from rough strips and survive heavy flak. Early jets were temperamental, fuel-hungry, and needed long runways. The F-51D Mustang, redesignated after the Air Force split from the Army in 1947, was pulled out of storage and sent to war within weeks. Pilots quickly found it ideal for close air support, hauling bombs, rockets, and napalm while enduring battle damage that would cripple a jet. Its rugged Merlin engine and strong A-frame made it perfect for forward bases. Mustangs flew 62,607 combat sorties in Korea, losing 351 aircraft, mostly to ground fire. Not bad for a design more than a decade old. But the Mustang's greatest surprise was its longevity abroad. Many smaller nations couldn't afford jets or the infrastructure they required, but they could operate Mustangs effectively with minimal resources. The Israeli Air Force flew P-51Ds during the 1948 Arab-Israeli War and kept them in service until 1961. The Dominican Air Force flew them until 1984, yes, 1984, 4 to 4 years after the prototype's first flight. These weren't museum pieces or airshow relics. They were operational combat planes flying patrols and counterinsurgency missions. The fact that developing nations could keep the complex Merlin engine running with limited parts shows how well-designed the aircraft truly was. Schmued himself moved on. After the war, he joined North American's Jet Division and became chief designer of the F-86 Sabre, the swept-wing fighter that dominated MiG-15s in Korea. If you look closely at the Sabre's design philosophy, you can see the Mustang's DNA everywhere, emphasis on visibility, aerodynamic purity, and range. The Sabre wasn't a Mustang with a jet engine, but it carried forward the same obsession with drag reduction and structural precision. Schmued retired in 1960 and passed away in 1985, having lived long enough to see his 1940 Impossible airplane still flying in combat 4 decades later. Few engineers ever witnessed that kind of legacy. The Mustang's influence extended far beyond fighter design. The NACA 45-100 laminar-flow airfoil that Schmued risked everything on became the cornerstone for later research into supercritical wings use on modern jets. In the 1960s, engineers studying transonic flight realized laminar-flow principles could delay shockwave formation at high subsonic speeds. Boeing applied those lessons to the 737 and 747. Airbus used them on the A320 family. Every time you board a long-range, fuel-efficient airliner, you benefit from aerodynamic truths Schmued proved at 400 miles per hour in combat with bullets flying. The P-51 Mustang demonstrated something military planners still struggle to grasp. Sometimes the best solution comes from an engineer no one asked, solving problems no one thought possible on a deadline everyone thought insane. Schmued's 120-day miracle in 1940 produced an aircraft that shaped aviation for generations. That isn't just engineering. It's vision realized under impossible pressure. The bombers reached Berlin and returned because one German immigrant refused to believe physics had already drawn the limits of flight.